Hi guys. Just let me know if you guys can hear me before we start, please. All right. So I did get a copy of the paper today, right after the exams, right, and I can safely say that that exam was pretty good, right. A lot of the questions, right, felt like they were repeat questions, right, especially number 6. There may be one question that some of you may have had a little challenge with, right? And it's a 6-mark question, right? Other than that, the paper was pretty good, right? The paper was pretty good, right? Um, so let's have a quick run through of the questions that actually came, right? So this first question here, this is a repeat of something that they brought previously, right? I didn't work this question yet, so let's do it together. A group of students conducted an investigation to determine the products of electrolysis when dilute aqueous copper 2 sulfate was electrolyzed with copper electrodes, right? So basically, this is what we have here. So we have an electrolyte, right? And right, so typically this is what I would do if I'm trying to figure out what's happening here, right? So we have our aqueous copper 2 sulfate, which is CuSO4, right? This is your anode and this is your cathode here, right? What are we using? We're using copper electrodes, right? So you need to take notes of these things here, right? Copper electrodes. So the following steps indicate the procedure. So the copper cathode was first washed with distilled water, right? So the cathode we're talking about here is this here, right? That's your cathode. So they said that it's first washed with distilled water, dried and weighed, and then connected in a suitable circuit, right? So this is the circuit here. A current of 0.2 amperes was passed through the solution and the starting time recorded. After 5 minutes, right? So we have this thing running for 5 minutes here, right? The switch was turned off and the cathode was removed, rinsed with distilled water, dried in air, and then weighed. The cathode was returned to the circuit and the process was repeated, recording the mass of the cathode at 5-minute intervals. So basically, every 5 minutes, you take out the cathode from the circuit and you weigh in the cathode, right? After each interval, the cathode was rinsed with distilled water, dried in air, and weighed until a total of 5 readings were taken, right? So now, the first question here is to define electrolysis, right? We have to define electrolysis. So this is pretty straightforward here, right? So instead of me writing, I'm just going to use some boxes here. Right? So electrolysis, right? Is simply, right, the decomposition of an electrolyte, right, by the passage of an electric current, right? So basically, if you pass an electric current through an electrolyte, it is going to decompose, right? That is what electrolysis is, right? State the difference between the anode and one difference between the anode and the cathode, right? Well, the anode, right, is the positive electrode, right? So you can say something as simple as this, right? And we can say that the cathode is the negative electrode, right? Something as simple as that should be able to get you your marks, right? 1 mark. The next part now, complete the table by recording the mass of the cathode, right, after 10 minutes and 20 minutes, right, and the mass of the copper deposited after 15 and 25 minutes, right? Let's try to understand this table here, right? So at time t equal to 0, right? This here is the mass of the cathode, right? So that's the mass when nothing has happened as yet, right? After 5 minutes, right, we have gone to 11.3. So therefore, all we did was take 11.83 and subtracted 11.8. That's how they got this, right? Now, for this next one here, we know the actual mass, right, is 0.05, right? So we want to know what is the mass after 10 minutes, right? So therefore, all we need to do, right, in this case here, we are going to add, right? So this is going to be 11.83 plus 0.05, right? And this here should be how much? Is that making sense? All right, that's 11.8. Right, so for this one here, I'm getting 11.85. Right, now this one could be a little confusing here for some students here, right? Because the actual mass deposited here, you actually keep going back to the original mass of the cathode. So that should be 11.85 here, right? Then when we go from at this one here at 15 minutes, you have 11.87, right? And this here is 11.8. So this here is going to be 0.07, right? And then for this one here at 20 minutes, right, the actual mass is 0.09. So therefore, this here is going to be 11.89, right? And then the final one here is going to be, that's 11.91, right, minus 11.8, right? And this is going to be 0.11, right? So you have to kind of be careful how you work this out, right? In terms of the numbers, right, you should have noticed that these numbers here, they increase sequentially. And the same thing for this one here, right? They're increasing sequentially. So you have to be careful how you're going to do the subtraction, right? All right, I hope that kind of makes sense, all right? And I'm sure we're going to have to plot a graph in a sec, right? So let's see first of all. All right, so you want to complete that, right? That's part 2. All right, so we're going to plot a graph here, right, using the data that we have, right? So let me just get this data across here. All right, so this is the data, right? And what do we actually want to plot? All right, so we have time in minutes, right? And you want to plot, what do we have here? Actual mass, right? So it's actual mass you're plotting it, right? So that means you're using this here, right? You're using this time and you're using actual mass, right? Let's look at the scale here, right? So we're going from, this is 2, 4, 6, right? So this here is 2, 4, 6, and 8, right? So we're going to use that there. So at 0, right, the actual mass of copper, right, deposited, well, we have no copper deposited in the first line, right? So you don't need to plot this one. So this one here is after 5 minutes, we have 0.03, right? So 0.03, right, is going to be here. So this here, now for chemistry, they like the dot on the circle, right? So I'm going to use the dot on the circle. So this here is your first point, right? So that's this point here plotted. The second one is 10 minutes against 0.05. So 10 minutes against 0.05 is going to be here, right? The next one is 15 against 0.07. So that's 10, 12, 14, 15. So that's somewhere here, right? The next one is 20 against 0.09. So that's here. And then the next one here is 25 against 0.11, right? So that's 22, 24, 25 against 0.11, and that's going to be about here, right? So we kind of expect to get a straight line. So let's draw the straight line. Right, so this is what our graph should look like, right? That's what our graph should look like, right? All right. All right, the next part here, right? The next part here, they said, use your graph to predict the mass of copper that would be deposited after 28 minutes. And they want us to use dotted lines to show this, right? So we need to locate 28 minutes on the graph, right? So the first thing we need to do, right? Let me get a line here. So they want dotted lines, right? So make sure you would have drawn right, so we're looking at 28 minutes, right? So this is 22, 24, 26, 28, right? So 28 minutes is somewhere here. Right, now we need to go across. Right, now remember, you might get an answer that's slightly different, because if you notice this kind of, right, this copy of this paper kind of warped here, right? So if you all get something like around 0.12, right, or 0.121, right, that'll be the answer, right? So maybe about 0.12 or 0.121, right? This graph paper is a little warped, right? But what you're going to do here, you know, this is 2 marks, right? So again, 1 mark for drawing your dotted lines, yes, right? And after 28 minutes here, right? So the answer will be about 0.12 or 0.121, right? So 0.12, right, grams, or 0.121, right? This graph is a little, the copy is not a good graph, right? So slightly off. Right? So that is the answer for that part. And they said write an ionic equation for the reaction at the cathode, right? So remember, this is your cathode here, right? Now the cathode is your negative electrode. When it comes to aqueous copper 2 sulfate, so CuSO4, right? The ions present in solution would be Cu2 plus, SO4 2 minus, right? We also have H plus from the water, and you have OH minus from the water as well, right? But in terms of what's happening at the cathode, which is the negative electrode, right? So yeah, so at the negative electrode here, what's going to happen is that positive ions, right? Positive ions are going to be produced, right? So these ions here, Cu2 plus and H plus are going to migrate towards the cathode. But what is actually being deposited at the cathode is Cu2 plus ions, right? So we have Cu2 plus, right? And this is an aqueous, right? But this is going to accept 2 electrons in order to produce copper solid, right? So when they ask us for the ionic equation, that's the ionic equation that they're looking for here, right? Right, so that is that part. What else we have here now? All right, so this part here, they want us to calculate the quantity of electricity that passed through the copper sulfate solution when 0.2 amps of current flowed for 20 minutes. Well, look, they even gave you the formula to use, right? So Q is equal to I multiplied by T. Right, so the current in this case here is simply going to be 0.2 amps, and you're multiplying that by 20 minutes. But you have to remember, when using this formula, it has to be in seconds. So you have to take the 20 minutes and multiply by 60, right? So this is going to be 0.2 multiplied by 20 multiplied by 60, and you're going to get 240. So we're talking about charge here, so that's coulombs, right? 240 coulombs, right? Right? And see some people asking about the graph. This graph is a perfect straight line. All of the points will pass through that straight line that you plotted, right? Based on this data alone here, right? If you look at the numbers, it'll be a perfect straight line, right? All right, so that's the charge that is flowing through the circuit. What do I want now? Calculate the number of moles of copper that would be formed, right? Calculate the number of moles of copper that would be formed. Now the thing is, what we're going to do here, we're going to take we're going to use this part here, right? I'm going to use this because this is what I just asked about, right? Even though in the data, in the table, they went up to 25 minutes, right? Since it asked me to work out for 20 minutes, I'm going to use the 20 minutes here, right? Calculate the number of moles of copper that would be formed. So let's go back to our equation at the cathode, which is Cu2 plus 2 electrons produces copper solid, right? Now, the question is saying calculate the number of moles of copper that would be formed, right? Now, according to this equation here, right? According to this equation is saying that 2 Faradays produces 1 mole of copper, right? That is what that equation is telling me. 2 Faradays, because you have 2 moles of electrons here. So what we need to do, let's convert this into coulombs. So 2 by 96,500 coulombs, right, will produce 1 mole copper, right? So I'm getting this straight from that equation there. Therefore, right, the charge that we just calculated there was 240 for this 20 minutes. So this is going to be 240 coulombs, right, will produce what? Right? So those of you who attended my chemistry classes will know that we just take this number here, multiply by this number, and divide by all of this here. You cross multiply. So this is going to be 240 multiplied by 1 divided by 2 by 96,500. Right? And this is going to give us 240 divided by, open brackets, 2 by 96500. Right? And we're getting a small amount of moles here, right? So I'm going to write it in standard form. 1.24 by 10 to the power 123. So this is minus 3 moles. Right? Now you didn't have to use standard form here, right? But I don't want to round off too early, right? That's why I'm doing this, right? Right? So that's the answer for that part there. This next part here, we want to calculate the mass of copper that is formed. So they gave us the relative atomic mass here, right? So 1 mole copper, right, has a mass of 64 grams, right? So 1 mole copper has a mass of 64. So we're going to take the answer we just got, which is 1.24 by 10 to the minus 3. So 1.24 by 10 to the minus 3. Right? And again, you're going to cross multiply. So you're just going to take that 1.24 by 10 to the minus 3. You're going to multiply that by 64 and divide by 1. So when I multiply this, I'm getting about 0.0796, right, grams of copper. Right? So we just take the answer we got from the previous part and we work that out. Right? And then this part here now suggests a reason for the difference between the mass of copper that we just calculated and the mass of copper in the table. Now the mass of copper that we calculated, right, is 0.0796 grams, right? This is what we calculated. But if you go to the table, right, this time here was for, how much it was? 20 minutes. So if you go back to the table, right, your 20 minutes here, right, that corresponds to a mass of 0.09, right? So this here is 0.09 grams, right? So this here is your measured, right? And this is your calculated, right? Now the question is saying, suggest a reason for the difference between the mass of copper obtained and the mass of copper recorded. So this is the actual measured here, right? And you'll notice that this number is actually bigger than the calculated. So that means we're getting some extra, we have some extra mass inside it, right? And that could occur for different reasons. If you read the procedure, right? If you read the procedure said that they washing with distilled water, they drying, and then they weighing, right? Now the thing is, if it was not dried completely, if there's any water whatsoever inside there, it means that my measured mass is going to be greater than the calculated mass. So one, right, the cathode was not completely dried. That's one obvious answer, right? Cathode was not completely dried. Right, that's one possibility, right? The other thing is that we know it's a copper 2 sulfate solution, right? But if there are any impurities in that copper 2 sulfate, right, you may have other ions that may be forming on the cathode, right? So impurities, right, in the electrolyte, right, as a possibility, right? But the more likely one is this first one here, right? The cathode was not completely dried, so therefore when you measure the mass, obviously it's going to be less, right? All right, let's see what people are saying there. Yeah, that's only one mark, eh? That's only one mark, so... Somebody said the cathode wasn't washed properly. Yeah, any reasonable answer that makes sense, well, you'll get a mark, yeah? So don't stress too much. That's just a 1 mark, right? All right, let's see what the last part of this question is here, right? So a sample, complete table 2 by writing the observations for each test carried out, right, on salt S. So we have a sample of salt S and it's heated strongly in a dry test tube. So you have some salt here, you're heating it. Moist red litmus is held at the mouth of the test, right? Moist red litmus. It turns blue, right? Let's see. Oh, sorry, no, sorry. Moist red litmus is, moist red litmus and blue litmus is held at the mouth. Okay, I didn't read it properly. So the first part says that an acidic gas is produced. So the litmus is going to tell us something about that, right? So all you're going to tell them here, if it's an acidic gas, it means that blue litmus, so this is the observation here. That's how you know it's an acid gas. So blue litmus turns red. Right, that's what you need to put for this observation here, right? The next thing that they have here is that from the inference, right, nitrate ions are present. Now, if you look at the test here, all it did was heat this thing here, right? So the only thing that could tell us that's a nitrate is that you would have gotten a brown gas produced here, right? A brown gas is produced, right? And that brown gas here is nitrogen dioxide, right? That's what you could say here, right? So we're only looking at the observation. So the observation here will be a brown gas, right? Right, now the next part here, we are adding aqueous sodium hydroxide, right? Gradually until an excess, right? So the two bullets here would be gradually and until an excess, right? So when you add, we just want the observation. So they are telling us that we have zinc ions present. So therefore, we're going to get a white precipitate here. Right? White precipitate here is produced, right? And it is soluble in excess, right? So the white precipitate has to be soluble in excess, right? Right? So that's all. They just wanted the observations. That's what they wanted, right? Right? And that's it. That's the 25 mark question there that that they gave, right? Next thing here now. Phosphoric acid, right? So we have H3PO4, right? That's phosphoric acid. They give you the formula. It's a common additive in most soft drinks. So if you all like to drink Coca-Cola, right? H3PO4 is one of the ingredients in Coca-Cola. It reacts with sodium hydroxide and alkali to form both normal salts and acid salts, right? So they want us here, right, to define these things, right? That's what they want. They want a definition for an acid. So in this case here, all right, let's define an acid, right? So there are different ways you can define an acid, right? You can say an acid is a proton donor, right? That's one possible thing you could say, right? That's one possible answer, right? Or you can also say an acid is a substance that produces, right, hydrogen ions, right? Or you can say H plus. Right? So any one of these two here, right, should be able to get you a mark. It's only one mark, right? Next thing here, they want you to define, right, what is an alkali, right? Now an alkali, right, is a base, right? But if you all remember what a base is an oxide of a metal, right? So an alkali is a base that is soluble in water, right? That's basically what an alkali is. It's a base that is soluble in water. One mark for that, right? They want a normal salt, right? So the definition for a salt, right, is a substance, right? So a normal salt is this, right? Or a salt. Normal salt. Substance produced when all of the hydrogen ions in an acid is replaced with metal ions or ammonium ions, right? That's all you need to say here. That's what a normal salt is, right? Is one in which all of the hydrogen ions have been replaced with metal ions or ammonium ions. That's a normal salt, right? You have two kinds of salts. You have acid salts and you have normal salts, right? For this part here, write a balance equation including state symbols. So the fact that they said including state symbols here, right? That's why they have 3 marks for this, right? So if you don't put the state symbols, you're going to lose the mark. So you want to form a normal salt with phosphoric acid and sodium hydroxide. So let's start. Sodium hydroxide is NaOH, that's aqueous, right? Plus phosphoric acid. Phosphoric acid, they gave you the formula for this thing, H3PO4, right? And that's aqueous as well, right? And when this reacts here, right, that's an acid and an alkali. You're going to get a salt, and they're telling us we're getting a normal salt here, right? So in this case here, you're replacing all of the H. So if you replace all of the H, you're going to get Na3PO4, right? So if you replace all 3 hydrogen here with sodium ions, right? This here is going to be aqueous, right? Plus, you're going to get H2O as your product. So this is going to be H2O liquid, right? Now this equation, as it stands, now they said you want to balance it, right? All right. So let's see how we're going to balance this here, right? All right, let's see. So we need to let's put a 3 in front of this, all right? So that's 3 sodium, right? What else are we missing? So 3 sodium, 3 sodium. In terms of hydrogen, we have 3 hydrogen here, right? And 3, that's 6, right? So let's put a 3 across here as well. Let's see if that makes sense. 3 sodium on the left, 3 sodium on the right. For hydrogen, we have 3 and 3, 6. On the right-hand side, you have 3 and 3, 6. In terms of oxygen, you have 3 and 4, that's 7 on the left. And on the right, you have 4 and 3, 7. Right? So far, it looks okay. Right? And yeah, so that's it. That's a balanced equation here. We just need to put a 3 in front of the sodium hydroxide and a 3 in front of the H2. That's it. Right? Yeah, I have a 3 in front of the H2. Right? I have a 3 in front of the H2. There's a 3 there. Right? Look at it. We just need these numbers here. We need this 3 and we need this 3 here. That's what you need to balance it. Right? Right? So it's a 3-mark question. So you're getting 1 mark for all the correct formulas. That's 1 mark. You're getting 1 mark for all the correct state symbols. That's 2 marks. And the 3rd mark is for balancing. Right? So you can still manage to get a 2 marks here if you didn't balance it. All right, they said state the molecular formula for an acid salt, right, formed from the reaction between phosphoric acid and sodium hydroxide. So again, it is H3PO4, right, and you're reacting this with sodium hydroxide, right? Now remember, if you want to form an acid salt, you need to replace some of the each, not all of the each, but some of the each. Right? So let's say you replace 1. If you replace 1 of the each, you will end up with NaH2PO4. Right? That is one possible acid salt that we could get. Right? That's one possible acid salt. Right? Alternatively, you could probably get something like Na2. Let's say you replace 2 of the H's, you will end up with Na2H, right? PO4, right? That's another possibility, right? Because I said state the molecular formula for an acid salt. Any one of them possible here, right? Right, now they said write a balanced equation to show the formation of the acid salt. So I'm going to use this as my acid salt here, right? So let's start with NaOH, right? I'm not going to put the state symbols here, right? H3PO4, right? And the salt that I'm going to get here, I'm going to say NaH2PO4, right? Plus H2. Right? Now in terms of balancing this thing here, is it balanced? Let's see. Na. We have 3H on the left. No, sorry, 4H on the left. Right? What am I missing here? I have 2 and 2 is 4. PO4 is fine. 4 and 1, 5. Right? So this looks like a possible equation here. Right? A balanced equation to show the formation of the acid salt. Right? Now part D now. Alright, what they're saying here now. A solution of phosphoric acid, 0.05 mole phosphoric acid, has a pH of 4. Right? So the pH of the phosphoric acid has a pH of 4. Right? Now the same concentration of sulfuric acid now has a pH of 1. State which acid is stronger. Right? So stronger acid has to do with the pH as well as the degree of ionization. So in this case here, the sulfuric acid, it has a pH of 1. So the one that has a lower pH is the stronger acid, right? So it's going to be sulfuric acid or the H2SO4. right? So that's it for this part here. Part E, Jeffrey complains of pains due to excess stomach acid after consuming too much orange juice, right? So this question here is a repeat question. Name 2 acids present in orange juice, right? So we have citric acid, that's 1, right? So we have citric acid, right? That's 1 acid that is possible, right? We also have, right, vitamin C, right, which is ascorbic acid, right, or what we call vitamin C, right? So that's it, citric acid, right, or ascorbic acid, right? So that's what we could put, right? Right, so that's part E, part 1. Name the type of chemical reaction that takes place in the treatment of excess stomach acid, right? So this here is what we call acid reflux, right? And they want the chemical reaction, say the type of chemical reaction. So the reaction that takes place there is a neutralization reaction. Right, so it's a neutralization reaction, right? And they said state the chemical name or formula of 1 compound that could be used to treat excess acid stomach, right? So the chemical name or formula, right? So now this here is what we call an antacid, right? But the thing is, right, you have to be specific because they want the chemical name, right, or formula. So you can use calcium carbonate. That's one possible thing we can take in order to neutralize excess acid, right? They want the chemical name or the formula, so you can put that, and you could put, or you could put CO3, that's calcium carbonate. That's the active ingredient in something like Tums, right? Also, we can use magnesium hydroxide. Right, so you find this in milk of magnesia, right? So this here is MgOH taken twice. That's a possibility, right? Another possibility here is aluminum hydroxide. Right, and this here is AlOH taken 3 times, right? There's 1 mark here. Any one of these here could work as an answer, right? Right, they said chemical name, so if you all put antacid, they're not going to give you the mark though, right? Alright, hope you all doing alright there. Alright, let's see what we have here now. So that is the 3rd part, right? Alright, so this next part here now, the fun questions, right? Question 3, state 2 natural sources of hydrocarbons, right? So we can say petroleum, right? Or you can put crude oil, right? This is the same thing though, eh? So it's either or here, right? Right? You can actually put you can put coal as an answer as well, right? You can even put natural gas as well, right? right? So let us want to, right? This next part here, identify the process used in the oil and gas industry to separate the components found in a natural source of hydrocarbon, right? So what they're talking about here is fractional distillation. Right? So that's that, fractional distillation. The next thing here, right? They want us to name two fractions, right? Name two fractions that are obtained from the process of separating the components found in the natural source, right? So your syllabus actually says that we should have known, right? We're supposed to know three fractions, right? And once we know three fractions, we have to be able to give a use for each of them, right? So this is something you had to learn. So what I normally tell my students to do is learn the fraction that is on top, right? So in this case here, we can use the fraction on top is called refinery gas, right? So there are going to be multiple answers that you could give here, right? So refinery gas is the fraction that comes out at the top, right? What do we use that for? We can use that for cooking, right? That's one possibility, right? The next one that we could probably put there, right? We can put petrol, right? Or you can just go with bitumen if you want. So bitumen, right? And what do we use bitumen for, right? Paving roads, right? So you have multiple answers that you could give for this one here, right? Because you have various fractions. You all could have gone with petrol, right? And we use that as a fuel for cars, right? So there are options, right? There are much more options inside here that you could have used, right? Right? They said any fractions, eh? So you all can put whatever you want, any fractions. You have options here, right? Next part here. So methane and propene are obtained from the separation of hydrocarbons and both react with bromine, right? Now, for me, right, I need to write down the formulas for these two things, right? So methane, right, is CH4, right? That's methane. The next one here is propene. Right, now propene has 3 carbons, right, and it's an alkene, so it's going to be C3H6, right? So that's a chemical formula for each of them here. Now they said both of them can react with bromine. Write a balance equation for the reaction with methane and bromine. So if we start with CH4, right, plus bromine, which is Br2, right? Now they didn't ask us for any condition here, right? But we need UV light for this reaction to take place. So what's going to happen is a substitution. So you're going to replace, so they want one possible reaction here, right? So let's replace, or let's substitute one hydrogen. So you can get CH3Br plus HBr, right? That is one possible reaction here, right? So you can get bromomethane in this case here. That's one possibility. There could be more than one answer here, right? But this is one possibility. The second one, you want, now this one didn't ask for any state symbols. You will notice that, right? But the second one, write a balance equation, including state symbols, right? For this compound here. So it's propene. So propene is C3, right? H6, right? Now you all are supposed to know at least the first 5 members of your homologous series. So if it's C3H6, right, propene is actually a gas. So this here is going to be a gas, right, plus Br2, right? Br2, that's bromine. Bromine is a liquid, right? And what's going to happen here, this is going to be an addition reaction, right? And if it's an addition reaction, you're simply going to get C3H6Br2, right? And that's it. You're gonna get one product here, right? And in this case here, right, the state symbol, right, you could probably put aqueous in this case here, right? So what's actually happening here is that you have, this is your propene or your 1-propene, right? And when this reacts with Br2, what is actually happening here is that the Br is simply attaching itself across this here, right? The Br is attaching itself to each of the carbons here. So there's no other product. There's only going to be one product in this case here, right? Right? Let me see something. Am I missing? Okay, yeah, that's it, right? Right, so that's 4 marks there. The next part here, they said pentene, right, can exist as isomers, right? Pentene, right? So this formula here is C5H10, right? Now pentene here, right, is an alkene, and they just want us to draw, right, 2 possible displayed structures of isomers. Do they want us to name it? Nope, they don't even want us to name it. So you have free reign here. You can draw whatever you want, right? So if I were you, I would draw the first one as a straight chain alkene. So 1, 2, 3, 4, 5, right? So that's 5 carbons. It's pentene, right? And then all we do, so this one is a giveaway, right? This is a giveaway here. So if I were you, I'll just draw this one as my first one. Right, so this is one possibility. Since it is an alkene, the easiest way to create an isomer is to switch the position of the double bond. Right, so all I'm doing here, I'm placing the double bond between the second and the third carbon. So that's 1, 2, 3, 4, 5. Right, you have to be careful that you don't draw 5 bonds around your carbons. Right. So this is one possibility, right? There are more isomers here, but I'm just going to draw these 2 for you here, right? If I were you, I'll go straight forward and give them something like this, right? Right, so that's it. That's the whole of question 3 there. That's it, right? This next one here is question 4. So element X is found in group 2 of the periodic table, and it reacts with chlorine to form a chloride, right? So we're talking about group 2 here, right? So before you do the question, you need to understand what is in group 2. So in group 2, right, you'll have to learn group 2 as a group as well as group 7. So we have beryllium, magnesium, right, calcium, right? So these are the elements that you have to look at, right? Beryllium, magnesium, calcium. So we just know this element X. They didn't tell us what it is, but it reacts with chlorine to form a chloride, right? Now group 2, right? So they said describe the type of bonds found in each of the following. So let's start with element X. Now element X belongs to group 2, and that is a metal, right? So element X here is a metal, right? So what are you going to say? You want to describe the type of bonds, right? So we have metallic bonding, right? So that's the type of bonding that we have here, metallic bonding, right? So in this case here, we have positive metal ions, right? Now positive metal ions are what we call cations, right? Positive metal ions are held together by a C, right? You can put this in quotes, right? By a C of negative electrons. Right? So that's it. That's all you have to say here regarding metallic bonding, right? So that is for element X, right? So element X, it belongs to group 2, so it is metallic bonding. Now they come and they ask us the chloride. So if you take element X and you react that with chlorine, so chlorine is a gas, right? Now element X here is a metal, and this chlorine gas here is a non-metal, right? So if you take a metal and a non-metal and you react it, you're going to get ionic bonding, right? So you're going to have ionic bonding present, right? So that is what is present here. So what you're going to see here, right? So positive, right? Metal ions. And when I say positive metal ions, this thing belongs to group 2. So therefore it is X2 plus, right? So positive metal ions, right? Electrostatically right, bonded, right, to negative ions, right? But when I say negative ions here, I'm talking about chloride ions, right? Negative chloride ions, right? Which is actually Cl minus, right? So it is ionic bonding. So what you have here, you will have X2 plus, right? And that's going to be bonded to 2 chloride ions, right? So the bonding that we have between these two here is what we call ionic bonding, right? So that's what they're looking for here, right? Right, so it's group 2, right? Beryllium, magnesium, calcium. Now they said write a balance equation including state symbols for the formation of this chloride. So this element here is in group 2, so it's a solid, right? Plus chlorine gas, right? And what you're going to get here is a compound, so you have to make sure you have the correct formula, right? So this is going to be XCl2, right? If you're all wondering how we get that, element X is reacting with chlorine. Element X has a valency of 2 because it belongs to group 2. Chlorine is group 7, has a valency of 1. So if you were to work out the chemical formula for this chloride, it'll be XCl2, right? So those of you who would have been in my class, right, should know how to work this out. So this equation, as it stands, that's it. There's no fancy anything to balance it, right? Make sure. Yeah, XCl2. And that's it, right? This here is going to be solid, right? Because it's an ionic compound, so we expect it to be a solid, right? 2 marks for this. All right, what else we have here? They want us to calculate the relative atomic mass of X. Now this question seems very familiar to me, so this could be a repeat wholesale. Calculate the relative atomic mass of X given that the molar mass of the chloride is 159. So remember, the formula is given by XCl2, right? So in this case here, let's so X, we don't know what it is, right? So let's call that X, right? Plus 2 chlorine, right? So this is going to be 2 by 35.5. Right? But when I add this up here, I'm going to get 159. So you have a simple equation here that we're trying to solve, right? So this here is going to be X plus 71, right, is equal to 159. So therefore, X is equal to 159 minus minus 71, right? So that's going to give us 159 minus 71. Right, and we're going to get 88, right? So that is the atomic mass of this element here, right? Now, what does that correspond to? Is that magnesium? Okay, so that's much lower down, right? That corresponds to, it looks like strontium. Make sure. Yeah, so this element here is actually much lower, right? It's much lower than these here, right? So it's actually, right, across here, right? So 88 should have been the answer, right? 88 should have been the answer, right? All right, element X also reacts with oxygen, right? The formula of the oxide that is produced, right? So again, you're going to get an oxide, right? So X plus oxygen, right? So the valency is 2 for the element X. The valency for the oxide ion is also 2. Whenever these two valencies are the same, we don't do anything, right? But the formula is simply going to be XO. That's it. That's all you need to do, right? For 1 mark. Right? All right, let's see. Now this is the only question that could potentially or could have potentially given you guys some trouble, and the reason why is because it is 6 marks. All right, so let's read the question carefully. The bonding in various substances account for the properties they display. Graphite is used as an inert electrode, whereas element X is not likely to be used as an inert electrode, right? With reference to the bonding, so that this is where you need to be careful now. So with reference to the bonding in graphite and element X, explain why graphite is used as an inert electrode while element X is not. So we already established that element X is low down in group 2. It's actually strontium. So in this case here, let's first figure out something here. So the bonding in element X, we knew it was metallic bonding, right? We said that in the previous part of the question, right? This is metallic bonding, right? Then we have graphite. Right, now the bonding that we have in graphite, so if you all remember what the structure looks like, right? So graphite has to do with hexagonal layers, right? So this is what the structure of graphite is going to look like, right? So we have these hexagonal layers here, right, that are covalently bonded, right? So we have, I'm just going to draw 2 layers here. They didn't ask us to draw it, right? I'm just showing you, right, what graphite looks like. Because they said in terms of the structure, right? And then we have these weak forces between the layers, right? That we call van der Waals forces. So we have covalent bonding here basically, right? Covalent bonding. Right? So this is one of the only questions here. Well, not the only, but one of the questions that could potentially cause some students to lose some marks, right? Because 6 marks. So there's a lot you could potentially see here in order to get some marks, right? Right, so let's start with the first one, right? So in graphite, right, the carbon atoms, right, are covalently bonded, right, in layers, right? So we have these hexagonal layers, right? And so basically we have the bonding, right, within the layer, right, are strong, right? Some people have the misconception that covalent bonds are weak bonds, right? But covalent bonds are actually strong bonds, right? So in graphite, the carbon atoms are covalently bonded, right, in layers, right? So we could say that each carbon atom is bonded to 3 carbons, right? That is what is happening in the structure. Every carbon, if I were to look at just say 1 carbon here, right, that carbon is actually covalently bonded to 3 carbons, right? So what that does, right, that leaves 1, so there is 1, right, free electron, right, for every carbon, right? So there's a free electron that's there because every carbon is bonded to 3 other carbons. So there's a free electron that is there for every carbon, right? These free electrons, right, are delocalized, right? And this allows, right, graphite to conduct electricity, right? So that is why graphite is able to conduct electricity, right? Now, even though, right, there are weak forces between the hexagonal layers, right? Yeah, so even though you have weak forces between the hexagonal layers, right, graphite, right, is, right, very stable, right, and unreactive, right? So that's the main reason, right? So they have graphite is very let's put chemically, right, stable and unreactive, right? So we're trying to say why we're using graphite as an electrode, right? It's a conductor, right? And therefore we're going to use it as an electrode, right? So since graphite is chemically inert, can be used as an electrode, right? So remember, we're answering this in terms of the bonding here. That's what we're doing, right? We're looking at it from the bonding. That's what they're talking about here, right? So everything that I've written here so far is for graphite. We're trying to explain why it's unreactive, right? And also why it's stable, why it's inert, right? And also why it's able to conduct electricity in this case here, right? So that's the main reasons here. Now, the thing is, in X, right? So in element X, right? Metallic bonding is present, right? So metallic bonding is present, right? And in this case here, we have positive metal ions, right? Held together by a C of negative electrons, right? So that's the bonding that we have in element X, right? This makes, right, element X, right, very reactive, right? So we need to say something else here, right? So it is metallic, right? So it's able to conduct electricity. So let's put element X bonding. We positive metal ions, right? Element X, right? So element X is a conductor, right? One second, I just want to change something here. Right, so we can say element X, right, reacts, right, by losing 2 valence electrons, right? Therefore, because of its reactivity, it cannot be used as an inert electrode. Right, now I'm just giving a comprehensive answer here, right? So this here is 6 marks here, right? So if you have much of what I have here, right, then chances are you're going to get some marks, right? But you need to talk about the structure. You need to talk about the structure of these two things here, of the graphite as well as the element X, right? right? So this is the only question here that really could potentially give you some trouble, right? So let's move on now. So this is number 5, right? Number 5 is organic again. And well, I have done this particular question so many times in my class. Everybody should have gotten full marks for this, right? So the question is asking, right? So they give us some organic compounds here, right? Give us some organic compounds, right? And they want what are the four characteristics of a homologous series, right? So this is a very common question, right? So same general formula, right? Similar chemical properties, right? Same general formula, similar chemical properties, right? Same functional group, right? What am I missing again here? Physical properties vary with the number of carbon atoms, right? That's another one there. Adjacent members, right, differ by CH2 units, right? And the last one here you could have put is similar methods or similar method of preparation, right? So they only want they only want 4, right? So these are 4. You could choose 4 here from the 6, right? That's basically what it is, right? All right, the next part here, they want you to state 2 uses of polyesters, right? So polyesters are compounds that contain the ester linkage. Now, one that you all had to learn for the exam would have been terylene, right? So terylene is a good example here. So terylene, right? But what do we use terylene for, right? So manufacture, right, of clothing, right? So all your school uniform and that kind of thing, right? That is what we use terylene for, right? So this is one possible use, right? Now, they want a second use here, right? So polyesters are also used to make plastic bottles as well, right? So there are some plastic bottles that are made from polyester, right? So plastic bottles, right? So a lot of those water bottles that you all use, right, to carry water to school, right? That is actually made of a material that is polyester as well, right? So any 2 valid examples, uses will work, right? The next part here, identify a test to distinguish between compound A and B. What is A and B? So compound A is C4H8. So compound A is an alkene, right? And compound B is an alkene, right? Usually they bring both in one question. So you want to test to distinguish, right? So there are only 2 acceptable tests. So we can use aqueous bromine, right? So you add aqueous bromine to both. Right, to both. Then we need to see what happens, right? So in the case of compound A, right? So compound A was the alkene, right? So we get rapid decolorization. Right? And when we say rapid decolorization, we get from reddish brown to colorless, right? That's your color change, right? In the case of compound B now, right, we get no color change, right? No color change, right? And when we say no color change, it stays reddish brown. Right? That's basically what happens here, right? Now, you have an alternative answer. You could have used acidified KMNO4, right? In which case, if we had A, right, you're going to get purple to colorless. So this is an alternative answer, right? I hope you all didn't do any kind of flame test. That's not what we're going to use for this, right? And B, it stays purple. right? So those are two possible answers. Either we use acidified potassium manganate 7 or we use aqueous bromine. That's it. From the list of compounds, right, identify, so the two things I want here, identify and draw the fully displayed structure of the alkene and the acid. So we already know what the alkene is, right? The alkene is A, right? So C4H8, so we have to draw it. So A is C4H8, right? And we need to say the name of this thing here, right? So this is 4 carbons, so this is 1 butene, right? So in this case, if I had to draw this, it would be right? So this is your 1 butene here, and that's your alkene, right? So they said, right, so this here is your alkene. Right. Next one here now, we want to see which one is the acid, right? Now, if you look at the formula, right? Where's the formula? So compound, this formula here is C4H8O2, and this one is C4H10O. Now, if you want to be an acid, right, you must have 2 oxygen atoms present to be an acid, right? This one here and this one here. So the only one that will give you that is compound C. So this C4H8O. So compound C, right? This is C4H8O2. Check back that there, C4H8O2. Yeah. So this has 4 carbons. So the name of this here is going to be called butanoic acid. Right, so that's butanoic acid. So let's draw butanoic acid. So you should have 4 carbons. 1, 2, 3, 4. You draw the acid group here. Right, so that is C4. That's 6 and 2, 8. Right, so this is it here. Right, so this here is your carboxylic acid. Right, or alkanoic acid. Right, so that's it. That's what I want there. Right. Right, so that's part D, right? And that's it. That takes care of number 5. Number 5 was pretty straightforward, right? All right, now this is one of those things, right? Even when I had my crash course, I told the students, hey, this is something you're going to learn the night before, right? Make sure you know this the night before, right? Because it's a lot to remember here, right? So in this case here, right? The first part, and by the way, this particular question here, green chemistry only came like probably about 3 times or twice, all right, since it's been introduced in the syllabus, right? So they want you to first define what is green chemistry. So there's a repeat question, wholesale, right? What is green chemistry, right? So green chemistry, right, is the design, right, of chemical products, right? Now it's not just products, right? Products and processes, right, that reduce, right, or eliminate, right, the use and generation of hazardous materials. Right? That's basically what green chemistry is. So you should have learned that definition, right? It's something you should have learned beforehand, right? But that's what green chemistry is. The next part says to list 2 principles of green chemistry. Well, they made it kind of easy here because when it comes to green chemistry, right, we have basically 12 principles of green chemistry, right? So there are 12 principles of green chemistry here. and you have a choice, right? You can decide what you want to, which one you want to use, right? So in this case here, right, give me 1 sec here. Right, so you have like several principles that you could use, right? They said list 2 principles, right? So you have 12 to choose from. You can put any one that you want, right? So one is to, they just said list there, prevent waste. That's a possibility, right? Maximize atom economy, right? So there are several you could choose from, right? This is, you basically have free reign here, whatever you want to do, right? Design less hazardous, right? Chemical synthesis, right? What else we have here? Design safer chemicals and products, right? Right? And you have a whole set, right? So you have 12 to choose from. They just said list 2, and they said list there. So which means you could just put a one-liners here and you'll get the marks, right? Right, so that's 2 marks here, right? Now in this piece here, right, they're telling us, right, a factory. So this particular question here, the description is very, they basically repeated the description here, right? So a chemical factory produces pesticides, plastics, and fertilizers, right? All of these things are bad things, right? Using synthetic raw materials. The factory, right, which has been in operation for 5 years, is located near agricultural lands. Residents of the community near the factory have reported significant environmental effects from pollution, which has impacted local agricultural economy. After bringing these concerns to the attention of the factory, steps were taken to employ green chemistry principles to reduce these impacts, right? So the first thing says, state 2 examples of air pollutants, right? 2 examples of air pollutants that could have been emitted from the factory. So what you need to do, right? You need to basically look at what are they manufacturing. They're manufacturing pesticides, they're manufacturing plastics, right? And they're also manufacturing fertilizers, right? So they said 2 air pollutants, right? So one obvious one here, when it comes to fertilizers, NO2, right, is a possible, right, a possible pollutant. Nitrogen dioxide, right? Because this could contribute to acid rain, right? So this is one possible answer. Nitrogen dioxide, right? That's a possibility for sure, right? Now look at the products again. You have pesticides, right? And you have plastics, right? Now if you're manufacturing plastics, right, there's a good chance that you could get gases being produced here, right? So in this case here, you could potentially get things like HCl gas is a possibility, right? Hydrogen chloride, because if you burn some of these plastics, right, one of the products that we could potentially get here is hydrogen chloride, right? Right? Now you're manufacturing pesticides here, right? Now they said air pollutants, right? So you can also get things like let's say benzene, right, as a possibility, right? Now the thing is, any valid answer could work, right? 2 examples of air pollutants, right? Now the pollutants have to be based on what they are manufacturing, right? What else? It is possible, right? Let me see something here. They want 2, right? Any one of these could work here. That's fine. This next part here suggests 3 substances found in the products produced by the chemical factory that may have polluted the waterways, right? So in this case here, remember you're producing fertilizers, right? So they said 3 substances, right? So 1, nitrates could end up in the water. That's one possibility, right? That's from the fertilizers, right? So from the fertilizers, right? Now they said suggest. Yeah, they just want it, right? They don't want what is happening here. But I can tell you what can happen here, right? So you can end up with something called eutrophication, right? This is not required though, right? I don't think they want us to explain this. They just want to know what pollutants could be here. So nitrates could be a pollutant that leads to eutrophication, right? So it basically deplete the oxygen in the water, you kill the fishes, kill the plants, right? So that's one possibility, nitrates, right? You can also have pesticide residue, right? So pesticide, right, residue could end up in the water, right? And it could kill the fishes, right? So pesticide residue is a potential answer. You can also have, right, you're dealing with plastics here, right? One of the things that happens here is that you produce microplastic, right? So when you end up with microplastics in the water, that's very small particles of plastics, right? This could end up in fishes, right? And these things could accumulate in the food chain, right? So they just want 3 substances. Any one of these, well, these could work here, right? These could work here. I don't know if you all had any others, right? Right. I see some people saying CFCs, right? Yeah, CFCs is a possibility as well. CFC is a possibility here as well, right? Let me see your answers here. What else you all have? Right, carbon dioxide, carbon monoxide. What else? Yeah, NO2 is a possibility as well, right? So any one of these here, right? So these are the possible things that we can get here, right? And the final part here, clean air on the earth is approximately 21% oxygen. Oxygen gas can be prepared in the lab. Draw a label diagram of an apparatus that could be used for the lab prep of oxygen. So if you all don't know how you prepare oxygen, basically if we take hydrogen peroxide, so this is how we prepare oxygen in the lab, it decomposes to give us H2O, right, and oxygen gas. Right, that's basically what's happening here. Hydrogen peroxide, right, decomposes to give us water and oxygen gas. So this here is how we produce the oxygen. Now, what we do is that we catalyze this reaction by using manganese dioxide. So MnO2 is the catalyst that we use to speed up this chemical reaction, right? So let's see how we're going to do this. They want a diagram, right? So they didn't specify, they didn't say if they want dry oxygen. All right, they didn't specify how they want the oxygen, right? So this here, right? Now these diagrams here, you could have drawn it freehand if you want, right? Right, I'm just gonna put some stuff inside here, right? This here is your MnO2, right? Or the manganese dioxide. Right, now what's happening here now? So we have, so you're already putting manganese dioxide inside your container here, right? So we need to put, right, so we need to put like 2 tubes inside here. Right, so let's lock this up so that no gases escape. All right, now on this one here, you can use a Tissot funnel, right? So what we're gonna do here, you're gonna put your hydrogen peroxide here. So this is your H2O2, right? So that's your hydrogen peroxide here that you're pouring inside this container here, right? And then what we could do, right? You can actually collect this gas, right, above water if we need to, right? Like I said, there are more than one way we can collect this gas, right? right? And this here could be water, right? And this here is where you're collecting the oxygen gas, right? So this is your bubbles of oxygen gas coming out here, right? And that's it. A simple diagram like this is what we're looking for here, all right? So it's hydrogen peroxide, right? You're using MnO2 as your catalyst, and that's it, right? So, like I said, guys, right, this was a pretty straightforward paper, right? There were lots of things that repeated here, right? There were lots of things that repeated, right? So, guys, I'm going to log off here, right? So, I hope these answers were helpful to you all, right? So, enjoy the rest of your night. Be safe, right? That's it for me here, guys. Enjoy. Later, people. Right? Don't forget to hit like and subscribe, right? Don't forget to hit like and subscribe.